Hey everyone, good afternoon. My name is Daniel Jepson. I am a SDR group manager with National Instruments working on USRPs for the last couple of years. Absolutely loving it. This has been kind of a wild ride. Dan Baker, who gave the last presentation, and myself have been working to define what synchronization means on a hardware level. And it is an honor to be able to be up here and to talk to you all about some things that we've discovered along the way, some pitfalls that we discovered, also some tips and tricks on how you can get the most out of your SDR equipment. And so without further ado, we're going to jump into what these RF systems look like that Dan was talking about from an LO standpoint, from a baseband standpoint. So using one of his examples that Dan brought up, this 5G massive MIMO testbed, we have 64 of these X310 devices in this rack. And that is incredible. And looking at it from this side, I'm like, man, that is really sweet. We got all those antennas. This looks really fancy. We got a lot of RF bling going on here. But what I want to do in this presentation is actually take this rack and turn it around and look at that rat's nest of cables in the back. That kind of explains how all this magic works from a baseband perspective as opposed from the cool RF perspective. So taking one of these devices out of the rack and kind of looking at it, this is the same block diagram that Dan had in his slides. We can see a couple different aspects of this. We have the RF subsystem that Dan talked about at length. We have our LOs, we have our front-end processing, we have our DSAs, our filters, our mixers, and all that. And then we get to the stuff that I deal with a lot on a digital basis. And that's the ADCs, that's the baseband clocking, that's our data movement, FPGA or ASIC. And I want to go through three areas here that I'm going to expound upon a little bit later in the presentation. The first is the reference clock input and fan out. So we have, like Dan mentioned, our most critical buffer in almost the entire design is where we receive this 10 megahertz reference clock coming into the device. And then the fan out, that goes to a couple different places. It goes to the converter PLL, the converter clock PLL. So this is the clock that drives our ADCs and our DACs. It goes to the FPGA or ASIC for data movement. And then it also goes to our LOs and does our RF synchronization. The second part of this is the converter clock PLL, so that takes the reference clock, multiplies it up to whatever rate that we're using. For the X310 devices, it's 200 megahertz, or sometimes 120 megahertz. And then the last part of this actually goes straight, or should go straight, into this bus interface device, and that is some sort of concept of time and triggers. So we've talked a lot about this conference about GPS. We've talked about PPS. And I'm going to go into that a little bit later on how we can use these things to great effect inside this device to make our whole system synchronization work out. So before we start with a rack of 64 USRPs, I want to take a step back and look at what it might look like to build this kind of development system just on a benchtop on my desk. Because whoever started with this gigantic system definitely did not start with 64. They probably started with 1 to get their basics right. So let's start with one X310 device here. We have a reference clock inside. We have a host computer that we're dumping all this data to. And throughout this presentation, I'm going to talk a lot about data movement from an ADC side. A lot of this applies just in reverse to the DAC side as well. So we're going to be dumping data from our USRP off to our host computer. And then we need an RF signal to feed this device as well. So we can see if the whole chain, all the way from RF through baseband and then back to the host, actually works out as we expect it to. First thing I want to do is introduce a couple different ways of viewing synchronization. The first is we can look like an oscilloscope just straight at the clocks. So we have a reference clock up here in green. That's 10 megahertz, moderately standard across industry. And then we have our converter clock for our PLLs, or coming off of our converter clock PLL that drives our ADCs and DACs, and that's at 100 megahertz in this example. So another way of looking at this is if we look at data in the time domain. And so here is our sine wave that's inherently really hard to draw in PowerPoint. And this is kind of trivial. It's one device. We're going to look at this on our host computer, and we're like, woohoo, we got a sine wave, right? But this doesn't tell us anything about synchronization. So we're going to skip past this, and I'll come back to this a little bit more later as we look at how we can build a couple devices in here. So we got one device. Good job. We were able to prove out that we got data all the way through. We got data up to the host. Our RF is working. Our baseband is working. Awesome. Now let's increase our device count. For ease of prototyping, we're just going to use the internal oscillators in both. We're going to take one RF signal and we're going to split it, and we're going to drive that into both devices and see, hey, does the RF data we're getting back from both of these devices actually make sense? We're doing everything we can from an LO perspective to make sure our RF front ends are aligned. But now let's look at a baseband perspective and make sure all of our converters are sampling this signal synchronously. So we have our oscilloscope view here. We're looking at our first reference clock. It's solid. We look at our first device clock. It's locked to our reference clock. Yay. We're looking at our second reference clock, and it's actually offset from our first one, which kind of makes sense, right? They're two different clocks, or they're two different oscillators and two different devices operating at two different temperatures. But then we keep triggering on this first reference clock, and we're actually going to see the second one start drifting with respect to it. And again, it kind of makes sense. They're different oscillators, different processes, different manufacturing, probably different voltages, definitely different temperatures. And so we're going to see the device B reference and converter clocks actually drift back and forth here. So from an RF perspective, when we're looking just at RF data here, we're going to see a very similar effect, where if we're triggering on the device A's data coming in, we're actually going to see the device B's data shift with respect to that back and forth as the oscillators warm up and cool down and do whatever else they do. So we have some problems here. The way to solve this, as you might have guessed, let's add, there we go. I have a remote, I forgot about that. Let's add a splitter to this, and let's add another splitter, and let's actually take a single reference clock and split it to both devices, right? So shared reference clocks, that makes sense, especially from an LO perspective. That's also going to make sense from a baseband perspective. So taking this, we're going to add in an external reference clock source to both of these devices, split it to both devices, and let's see what that looks like from an oscilloscope view. So now we have a single reference clock. We're triggering on one of the edges of our 10 megahertz reference, and voila, both of our device clocks line up. And just because I don't believe this yet, we're going to run this a couple times and try over reset cycles, power the whole thing down, power it all up, and see what happens. Okay, so it shifted a little bit. The second device clock shifted a little bit. Really can't tell because it's all periodic throughout here. And we're going to try it again. Okay, great. From this perspective, we have aligned reference clocks. But let's look at it from the RF perspective, and let's look at the RF data coming back into the device. So here's our first signal coming in. Uh-oh, we're off by a converter clock. That's interesting. So I'm going to try it all again, because I don't believe it again. And I'm going to, we're off again by another converter clock period. And this is actually going to continue ad nauseum all the way down in one converter clock segment. And this is because we don't have the concept of time yet in the system. So device A is over here saying, I'm going to start acquiring now. And then device B maybe has a little bit of latency in the link and says, oh, I'm going to start acquiring now. Those two are going to start at completely different reference clock or converter clock edges. Even though on the oscilloscope view they're all lined up, whenever we're triggering a start and a stop acquisition on both devices, we have no idea, we have no concept of time on our SDR devices, and therefore we can't have synchronous captures like this in the RF domain. Now, post-processing, you could totally go back and collapse these on top of each other if it really is periodic, but that only works for periodic test tones like I'm using right here, and not for real-life signals. So, before I get into the solution for that, let me present another problem. Up until now, we had a very uniform 10 megahertz, 100 megahertz relationship between our reference and our converter clocks. Let's make this a little more interesting. Let's go with a 25 megahertz converter clock. What happens here is device A may have started its PLL with respect to this first reference clock edge. If we add another device on here, it may have started its PLL with respect to a different edge of the clock. And because we have now introduced a higher R divider value inside of our PLL to make the relationship between 10 and 25 megahertz work, we're going to have 180-degree phase ambiguity between all of our reference clock, or all of our converter clocks all the way down. If we add more of these devices, we're going to see some line up with device A, some line up with device B. What this looks like in our sampled waveforms is we're going to see a half a converter period offset. Now, because this effect actually compounds with the effect of not knowing when we can start and stop our acquisitions, this is going to repeat itself every converter period all the way down. So I didn't draw it here. I just collapsed all of those multiples of converter clock periods all the way down. So you're going to see a bunch of them stacked up at this half converter clock period offset. And that tells us we have 180-degree phase ambiguity, or 1 to 2 phase ambiguity. If we had an even more weird clock relationship here, so I drew 10 to 25 megahertz, if we had like a 10 to 122.88 megahertz, good grief, you're going to have a ton of those lining up, and you're going to be like, oh, it's not synchronized at all, when in reality it's just hitting these very fine quantization steps. So the solution for this, as we've hinted to throughout this conference, is add a PPS. Add some sort of time, add some sort of trigger concept. What a PPS does is it identifies a single reference clock edge on all devices. And let me go a step further. It needs to identify a unique reference clock edge on all devices. And so this is used for PLL resets. This is used for keeping a concept of time and a timekeeper on each one of the SDR devices. And because now we have timekeepers, we can actually start and stop our acquisitions at known times throughout. So if I have my two devices up here, and I say, all right, I want device A to start in 10 seconds, and I want device B to start in 10 seconds, I say go. They're just sitting there idling until that 10-second mark is hit, and then both start the acquisition at the same time. So adding to our system here, we're going to add in another component, and that is the PPS, or trigger input, to both of our devices here, split again. And we're only going to go to the RF domain this time. We have our first device. We're going to add our second device. We're going to run it a few more times, again, because I don't believe it yet. And they're all going to line up. Voila. Now, this is just benchtop testing at my desk for fun. I was like, well, I wonder what had happened if I ran this whole system, repeated resets, overnight. I'm like, okay, well. So I run it throughout the day. I get this kind of results. I run it overnight, and I get something that looks like this in the morning. I say, well, shoot. What's going on here? Well, to save you a very long debug story, the temperature in our building actually increases overnight because we like to turn down the AC so we conserve some electricity. What that does is change the temperature of my DUTs on my desk. And what's happening here, let me go back to digital basics, digital logic basics. Inside whatever FPGA, ASIC, DSP chip that you're using to capture this PPS signal, there is most likely a flip-flop. Oftentimes it is a rising edge flip-flop, and in our case, it's clocked by this 10 megahertz reference clock that we have. The PPS goes into the D input, the data input of the flip-flop, and this flip-flop, in any device that you can see, has a certain amount of timing associated with it. So here's a waveform on the right. We have our 10 megahertz. We have our PPS input. And in a lot of these systems, the PPS is actually driven from the host on the falling edge of the clock to keep it away from any rising edge effects that the flip-flop might have. Because the flip-flop has timing parameters for setup and hold. Again, this may be a review for some of you with digital logic. It has setup and hold times that define the keep-out region that we cannot violate. So if our PPS input, if our D input of our flip-flop is changing on or within this keep-out region, we are in jeopardy of not capturing the correct value. We don't know what the correct value is because it's changing right when the flip-flop is trying to capture our D input. And so what was happening overnight is we were really close. We were really close to the keep-out region. And maybe along the borders of this keep-out region, we're just barely violating setup or we're barely violating hold. The system's going to work 90% of the time. But as it heats up or as it cools down, we're going to see some variation in this, and we may need that entire setup and hold time not to be violated in order to actually run our system as we designed. So if that PPS input moves to the right into this keep-out region, all of a sudden our flip-flops can go metastable. We may or may not capture it on this rising edge of the 10 megahertz. We may actually see our PPS input one cycle later on the next 10 megahertz rising edge. And so that's going to contribute to this one reference clock period offset, and then because our converter clocks are 880 degrees out of phase then, we're going to have this additional half converter clock period offset on there as well. So kind of wrapping up with the PPS, timing between the PPS and the reference clock must be closed at the FPGA or the ASIC to control the device. And oftentimes these are numbers that are either published with the FPGA inside the SDR device and close that direction, or hopefully they've also published them at the ports of the device. So as you're connecting up your SMAs, you can be like, all right, I need to make sure whatever's driving these ports has this kind of timing relationship with respect to 10 megahertz and PPS. Couple practical implementations here. Drive PPS from the same clock domain that you're receiving it in. So it doesn't work if you have a GPS receiver here that's providing your 10 megahertz reference, and then at an extreme case, you just have a button over here, and you have your stopwatch, and you say, once a second. That is clearly not the right clock domain, and you clearly might get, you might fail setup and hold time because my thumb definitely isn't accurate. Obviously, that's probably not a case you're ever going to see, but even if you're driving it from 2 different GPS modules, you're not guaranteed to have tight timing there, even if you're using a 10 megahertz clock and you have 100 nanoseconds, a window to kind of hit this in. The other practical implementation is use the same topology. So we talked about daisy chain topologies for LOs. We talked about star topologies. So almost the best way to do this is a star topology where you have a single source fanned out to multiple receivers. So multiple SDRs, you have one source, and you have match length cables going to each one of those to allow you to close this timing as accurately as possible. So we've done all this. We run this a gajillion times. We see everything line up very nicely in our time domain. We're really happy with it. We have about a nanosecond or so of drift or of variability in it, and that's okay for the most part. Oftentimes the target I'm shooting for is a nanosecond or less for baseband synchronization, and that allows the RF guys to build on top of that with their RF synchronization. Some things that can actually help decrease that 1 nanosecond to even less. Try to keep your devices at a constant temperature. I've kind of harped on temperature quite a bit. Temperature can introduce a lot of drift, especially in LOs, but also in buffers on your board. So if you're a hardware designer, choose low propagation delay different buffers. So as your device warms up or as your buffer warms up, you want to keep that propagation delay fairly constant over temperature. There's a couple great buffers out there that have like drifts in like the femtosecond range per degree, which is fantastic. Close timing, like I just said, but also, so pay attention to the timing between your PPS and your reference clock coming into your FPGA or ASIC, but also pay attention to closing timing at your PLL. So the reset pin of your PLL that boots all of these devices up synchronously is going to have these same kind of setup and hold parameters associated with it, and you need to make sure you meet timing there and at your FPGA in order to get deterministic timing all across the board. And then remember to account for variations in your reference clock distribution. So oftentimes we don't think about this, but if I have a device that distributes a single PPS to multiple devices, that device in itself is going to have some sort of inherent skew between all of its outputs. And we need to account for that in our total budget for our baseband synchronization. All right, going briefly into geographically distributed systems. This has also been mentioned. Well, this hasn't. I don't recommend this. So the first way to do this, like if we were in like kind of a scale of this room, very, very long cables. So if I had an SDR device all the way over here and another one, say, up here on the podium with me, I could theoretically connect them with very long SMA cables. This only works practically in like the meter, maybe low tens of meter range, because you're going to get skew within your cables, you're going to get temperature differences, the bend radius of the cable, if someone walks up and bends the cable all of a sudden, you're going to get a little bit of propagation delay difference in that as well. And all devices must have length match cables in order for your reference clocks to be aligned. So if I have a device up here, I'm using a device over in the corner, I'm just also going to have a stack of cable right next to me and this device, while that one is going to be stretched tight to get across the room. So this is practical for a few meters, but not much beyond that. GPS. So advantage here, it's worldwide. Once it's locked to a satellite, it actually inherits the accuracy of the satellite's oscillator, which odds are really good that that satellite has a whole lot better accuracy than your oscillator, especially built into some of these lower-end SDRs. However, the downside here is alignment is typically poor compared to cabled synchronization methods. So we're looking at like tens of nanoseconds here, as opposed to less than 1 nanosecond of accuracy with cabled methods. White Rabbit. I've heard there's a super interesting talk that includes White Rabbit tomorrow. I don't know who you are, but I've heard rumors of this talk. I would love to, I'm looking forward to hearing it, so I'm just going to give a very brief introduction to what White Rabbit is. It's an Ethernet-based standard. It kind of goes up to 10 kilometers, although I've heard rumors of much longer runs than that. It uses optical cables, specialized transceivers, and it essentially combines two different technologies. One is an extension of 15.8 PDP for time references, and then also Syncy for actually distributing your clock reference to each device. And we recently incorporated it in the N3XX family of devices, so the N310, N320, N321, and we were able to get typical performance of less than a nanosecond across 5 kilometers of cable difference. So the setup that we tried is we had this 18-port White Rabbit switch. I had a 1 meter cable going to one N320, or N310, pardon me, and then I had a 5 kilometer spool of cable. It was kind of cool. Everyone walked by my desk and said, "What are you doing?" And drove both of the outputs of this device to an oscilloscope and measured the time delay difference between them. And we saw, on average, about 200 milliseconds worth of alignment, and then a worst case about a nanosecond-ish. So, yes, I meant 200 picoseconds. Thank you. Yeah, 200 milliseconds. Typically, we're 200 milliseconds. Ideally, we're a nanosecond. Yeah, 200 picoseconds of alignment. To give you, when I started at NI, I was doing a lot of digital VNV like this, and at first when I saw a clock at 10 megahertz, I said, "Whoa, that clock is fast. We're in the nanosecond range." And then when I started working on synchronization stuff like this, I started measuring fast in terms of like, oh man, it's slow. It's like 10 picoseconds. And my perspective has really shifted as to what is possible. And technologies like this really demonstrate where we're going with some cool Ethernet standards, and where I hope to see that we continue to go down into where picoseconds are slow and femtoseconds are fast. And seeing that progression is really cool, especially over like basically a 5 kilometer difference of cable. So that was my personal aside. In summary, share your reference clock. If you leave here today learning nothing else, share your reference clocks, preferably with the same topology. Share a common trigger to get a common concept of time between all of your SDR devices. And then lastly, recognize that there's a lot of environment variables out there to correct for. One of the bigger ones is topology. Next biggest one is probably environment and controlling temperature variations between your devices if you want really tight timing. And the other one is know your equipment. Know what it's capable of. If you're designing equipment, watch out for all these pitfalls. Make sure you close time in different places. And if you're using equipment, know what your equipment is capable of and what is possible, both for your application as also for what you want to do with the device. So with that, thank you to GNU Radio for sponsoring a ton of hardware-centric talks for the whole afternoon. We really appreciate it. And if you have any questions, I'm happy to answer them and go more into this as well.
All right. Thank you so much, Dan.
I think I heard the question, and that was, does White Rabbit require Xilinx IP? It does not require Xilinx IP. It does require IP from CERN, I believe. Yeah, I believe they wrote most of it. It's all open source. I forgot to mention this. It's all open source. It's available online. When we integrated it into the N310 and N320, it was a breeze. We were able to download it, integrate it, and most of it just worked out of the box. You're going to need some sort of a master device. So one of the more intricate details of this is one end of the link at least requires calibration. Typically, it's the master side. All of our devices only work as slaves because they have not been calibrated. You actually need to calibrate it on a per bit file basis. So if you change your bit file in your FPGA, that actually requires calibration with the system as a whole. So yes, there are specialized switches. There are specialized master devices out there that you can buy. We used a couple of 2-port devices and then one 18-port, like very large switch to try a bunch of synchronization. Yeah, 7 Solutions. Yes, thank you. Is the manufacturer that we have gone with. And the app note that I had up there linked on the Edis page it calls out these 7 Solutions hardware as well. And I believe there's links that you can go check out their hardware. Yep.
Thank you very much.
Thanks.